Today we'll be approaching this problem 11 from Gunning's book. The question is, for any mapping f from A to B, we set two elements equivalent if, for those two elements, A1 and A2 within the domain A, that we have f of A1 is equal to f of A2. That is, as long as their outputs are the same, we set them equivalent to another. Our goal is to show that this defines an equivalence relation on the set A, and then show that the mapping f from A to B induces an injective mapping big F on the quotient space A quotiented against our equivalence relation. Please take a couple seconds to try this out. Then we'll be supplying some hints. Then we will close with the solution. All right, for some hints, to show that we have an equivalence relation, we need to remember the qualities, the axioms that equivalence relation must have. As a hint, there are 3 of them. Once you've done this, it's not hard to show that you have an injective mapping, but remember that a mapping is injective if either equal outputs imply equal inputs or unequal inputs imply unequal outputs, your preference. All right, let's proceed. So we'll recall that the 3 axioms an equivalence relation must obey are reflexivity, symmetry, and transitivity. So reflexivity is easy. If we can see that A1 is equivalent to itself because F is a mapping, so F of A1 will always equal F of A2. It will always equal F of A1 because it's a mapping by definition. For symmetry, if we have A1 equivalent to A2, then we have F of A1 is equal to F of A2, but equality is also an equivalence relation, so it also obeys symmetry. So that means that F of A2 is equal to F of A1. And then this means that A2 is equivalent to A1. Finally, for transitivity, if we have A1 equivalent to A2 and A2 equivalent to A3, then we apply the transitivity of equality in the outputs. So we would get that F of A1 is equal to F of A2, which is going to be equal to F of A3. And therefore we can just eliminate the middle component and get F of A1 is equal to F of A3. So we can set A1 equivalent to A3. With all of that, let's now show that this induces an injective mapping. And for that we were given 2 options. Either we could show that equal outputs implies equals inputs, or unequal inputs implies unequal outputs. Let's proceed with that second method while I erase this. So for unequal inputs implies unequal outputs, let's take 2 elements from our quotient space. Let's call them x, comma y, and these will be representatives of the quotient of the equivalence class associated with each of those elements. And we have that capital F of x is just going to be lowercase f of x. And this is and we have that f of y is equal to lowercase f of y. And these are unequal. And the reason this is because if they were equal, so suppose to the contrary that they were equal, then we would have that f of x is equal to f of y, so x and y would be in the same equivalence class. But our assumption at the first place was that x and y were from different equivalence classes. This provides a contradiction, so f of x and f of y are unequal, so big F of x and big F of y is unequal. Therefore, since we have unequal elements implies unequal outcomes, then we have an injective mapping capital F, and we're done. Thank you.